Hey, this is Kevin, and you're listening to Kevin's Math and Science Podcast, where I, Kevin Wallenstein, talk about the cool concepts, some interesting vignettes, and revolutionary ideas explored in science and math. This being the first episode, let me tell you a little about myself. My background is chemical engineering. I got a master's from Princeton, and before that, a bachelor's from the City College of New York. Well, that's enough about me. On to today's topic. So today's topic is diffusion. Why start with diffusion? Diffusion is one of those topics in science that in pop culture doesn't really receive the props it deserves. Everyone has heard of relativity and knows Einstein's work, but no one knows about diffusion, which Einstein also worked on. So to start, let's do a kitchen top table experiment. Let's drop food coloring into a dish of water. That food coloring spreads throughout the dish in a process known as diffusion. As a chemical engineer, I have to give you a more rigorous definition. Please forgive me. The phenomena called diffusion is defined as the movement of one chemical species through a mixture, in the fundamental text Transport Phenomena by Bird, Stewart, and Lightfoot. Why does this mixing occur? The dye could perfectly well just stay where it is and not diffuse. Well, the first clue came in 1827 in the lab of botanist Robert Brown. After putting pollen in water, Brown peered into the lens of his microscope, and to his surprise, the pollen was jumping all over the place. It would move in one direction and then abruptly change direction and move for a period in another direction, just to change direction again. What you are looking at now are simulations of 5 trajectories of randomly moving particles starting at the center, similar to what Brown would have observed. It would take nearly 100 years before it was shown that these randomly moving pollen particles could explain what we see in this dye water system. Then, in a seemingly unrelated event, in 1856, Adolf Eugene Fick discovered a law of diffusion that is still used. He showed that the flux, or amount of the diffusing molecule passing through an area, was equal to the gradient in concentration times a constant for a large class of systems. Yes, I did just put an equation on the screen. It's that important. This equation is called Fick's law, and in science, they teach whole classes on it. This constitutive equation plus a mass balance is all we need to describe a real diffusing system, like the dye in water that we were looking at. What you are looking at now are simulations of dye in water, using Fick's law and a mass balance. Notice that the concentration is trying to even out and the dye is dispersing throughout the system, just like the experiment. This is what science really tries to do. You make an experiment and then you try to develop a theory that explains it. And Fick's law really does a good job of explaining the experiment. In the experiment, we saw the dye diffusing throughout the water system and moving and trying to even out. And then we see the same phenomena happening in the theory. So far, we're in 1855, and we can pretty much describe diffusion, at least in our simple dye and water experiment. But what Fick couldn't explain is why that theory worked. 75 years later, and 100 years after Brownian motion was discovered, none other than Einstein showed why Fick's law worked when particles were moving with Brownian motion. He derived that in the limit of an infinite number of particles, that the independent random motion Brown discovered results in Fick's law. All the particles start at the center and then move slowly outward, randomly, and this random motion generates something really similar to Fick's law. You get a dissipation of gradients, and slowly the particles try to even out and concentrate homogeneously in the system. I think this really illustrates the beauty of science. Brown observed that particles move randomly. Then Fick showed that concentration gradients tend to dissipate via diffusion. Einstein showed that random Brownian motion is what causes diffusion. This was a huge breakthrough. You're relating what happens at the particle level to what we're seeing in real life. You may be thinking, who cares? Well, diffusion affects just about everything, from how oxygen gets into our cells to making a nuclear bomb. So hey guys, thanks for listening, and next week's podcast will be on Monte Carlo simulations.